When discussing the wave-like properties of electromagnetic energy, different types of electromagnetic energy can be distinguished using two properties. The frequency of the wave, which describes the number of times the pattern repeats per second, and the wavelength, which describes the distance between repeats in the wave pattern. Cycles per second has been given the unit hertz with the abbreviation Hz. As with many natural phenomena, these parameters vary over exponential ranges. The lowest frequency waves cycle at about 10,000 cycles per second. The highest frequency waves cycle at over 10 to the 21 cycles per second. The electromagnetic energy we perceive as light represents a small part of this large range. Different colors are electromagnetic energy with different wavelengths and frequencies. Red light has a frequency of about 4 times 10 to the 14 cycles per second, and violet light has a frequency of about 7 times 10 to the 14 cycles per second. Just beyond visible light on the frequency scale is ultraviolet light, then X-rays. Gamma rays have the highest frequencies. Moving from visible light towards the lower frequencies, there's infrared light, then microwave, and finally radio waves. Since the relationship between wavelength and frequency is known, we can represent the same scale using wavelength instead of frequency. Wavelengths range from over 10 kilometers for the longest radio waves to picometers for the highest frequency gamma rays. Looking at exponential patterns with scientific notation can make it difficult to see just how big these ranges are, so looking at some numbers using decimal notation may help. The longest radio waves cycle at over 10,000 cycles per second and are tens of kilometers long. The shortest radio waves cycle at tens of millions of times a second and are a few meters in length. As we move to higher frequencies and shorter wavelengths, we get into values well beyond our experience. Visible light waves cycle at tens of trillions of times a second and are less than a micron in length. At the far end of the spectrum, gamma rays cycle 10 to the 21 times a second and have wavelengths in the picometer range. Looking at a summary of these frequencies and wavelengths allow us to consider some practical implications of these numbers. Light microscopes are a common and powerful tool for much of scientific research, and the fact that they rely on electromagnetic energy in the visible range has implications for the level of resolution we can achieve using light microscopy. Light microscopes are able to resolve structures as small as 200 nanometers. It is no coincidence that this is right in the range of the wavelengths of the electromagnetic energy we perceive as visible light. Moving to longer wavelength microwave energy, we can find even more examples. Consider the cell phone. While cell phones come in a variety of shapes and sizes, they all share the need to send and receive cellular signals. To be used as a phone, they need an antenna matched to the wavelengths of microwave energy transmitting the signal. Most cell phone signals are in the 1 to 2 gigahertz range, giving them wavelengths of 20 to 30 centimeters. The need to have an antenna capable of reliably and efficiently receiving this signal places a limit on the minimum size of a phone. Cell phone antennas can be made smaller, but at the risk of reducing their effectiveness and increasing the risk of interference. Another ubiquitous use of microwave energy can be found in the kitchen. Most people have experienced uneven cooking in a microwave oven. This is due to patterns of interference as microwave radiation bounces around the inside of the oven. The space between the hot and cold spots in the oven is directly related to the wavelength of the energy used. Standard microwave ovens use electromagnetic energy at frequencies of around 2.54 gigahertz, giving them wavelengths of around 11 centimeters. The wavelength of the energy used by the microwave oven can be visualized by heating a few slices of cheese in a microwave. After a few seconds of heating, repeating hot spots will appear separated by about 1 wavelength. In addition to the range of wavelengths and frequencies across the spectrum, the amount of energy carried by an electromagnetic wave varies as well. Long wavelength, low frequency radio waves contain the least amount of energy, and high frequency, short wavelength gamma rays transmit the most energy. Based on this, we can extend the description of how electromagnetic energy varies across the spectrum to say that it ranges from long wavelength, low frequency, and low energy to short wavelength, high frequency, and high energy. Energies range from the picojoule range for radio waves up 15 orders of magnitude to kilojoules for gamma rays. The way electromagnetic energy interacts with matter depends upon the type of electromagnetic energy and the characteristics of the matter involved. The biggest distinction is between forms of electromagnetic energy that carry enough energy to disrupt individual atoms in a substance. This is called ionizing radiation and begins in the ultraviolet range. Electromagnetic energy at the low end of the UV range and below is non-ionizing radiation. Electromagnetic energy in this range primarily heats matter, raising its temperature, or temporarily alters the excitation state of individual electrons without removing them from the atom.